should be able to zoom in. Maybe that's just the... That's like almost readable, right? Is that basically readable? Just don't go any smaller. All right. So last time we talked about cars and coulters and conses. We also talked about lambdas. Let's kind of review that a little bit. So we have this function. Let me actually zoom out once. I'll just not let it go so small. All right, so we have a function called car. Remind me, what does car do? Okay, returns the first element of a list. So if I have a list, like the list 1, 2, 3, the car of the list 1, 2, 3 would give me that 1. All right, now let's see this kind of in action. I think I mentioned last time that I take you to the website for Dr. Racket. At least had the, I have a link up on Slack. Do I have it installed on here? Or I have a link up on Blackboard. Racket on here? Okay, I downloaded it last time during class. So let's go ahead and... So it's available for Mac and PC. This is going to be our scheme interpreter that we use. So it'll allow you to actually type this stuff in and do it. You're going to need it for your homework assignment for Friday, which is going to be some programming. All right, so while that guy is, well, it'll be done here in a second. Drag this guy down here. Okay, so here is Dr. Racket. Used to be called Dr. Scheme. Let's see if I can get this text bigger up here. Is that readable? All right. So, couple of things to understand about how Dr. Racket works is you have a real-time interpreter down here. So anything you type down here will get evaluated in real time. So for instance, if I say car of the list 1, 2, 3, like that, I have to choose a programming language. Choose language. So let's go teaching languages. Okay, I don't want to give you... screw it. Just choose advanced student. That should give us everything. I've already kind of blanketly said that you can only use stuff I've introduced in class, right?
So do you want us to use that advanced student too?
Yeah, it probably won't matter for most of the stuff. In fact, beginner student is probably going to be enough. But you have to pick a language that you want Dr. Racket to kind of, adhere to when you're doing your stuff. So I don't think it'll matter once we get into this. If I find something that it breaks, then I'll tell you which one to switch it to. But advanced student will probably be fine.
You're able to switch it even when you pick one?
Yep.
Okay.
Yeah, you can switch it again. So again, we'll do the car 1, 2, 3. Row. there's our 1. I had to restart the window by hitting run in order for it to do it. Okay, so car gives me the first element of a list. What does the cdr do? So cdr of 1, 2, 3 should give me what? The list 2, 3. So it gives me the rest of a list other than the first element. So there's the list containing a 2 and a 3. We also introduced a function called cons. What is cons used for? Constructing lists. Okay, it's used for constructing lists. Although technically what you just said is accurate. Let's actually see what the advanced language will do for this. If I do a cons 1, 2, okay, yeah, so it requires the second element to be a list, so it won't let you do the dot notation, which is what I advertised, so that should be correct. So a 1 onto the empty list will give me the list containing a 1. So you can construct a list using the cons function. And a lot of times you would use these in a nested way. So you would cons a 1 onto the cons of 2, onto the cons of 3, onto the empty list, which will give me the list 1, 2, 3. Because as this unwraps, I'm consing a 3 on the empty list, which will give me the list containing a 3. I'm consing 2 onto the list containing a 3, which will give me the list containing a 2, 3. Then I'm consing a 1 onto the list containing 2, 3, which will give me the list 1, 2, 3. That make sense? So those are our kind of, let's call 3 primitive moves that we might start with. I also mentioned, so we kind of go back to this idea that all, we think about programming languages. All programming languages have a way of facilitating facilities for doing memory, asking questions, and repetition. Okay? I've already mentioned that Scheme does not have a, in terms of the core language, does not have a way of doing loops. I think one of these languages might have a built-in loop function that somebody wrote, but we're not allowed to use it. So we have to do everything recursively. You'll thank me later. But in terms of defining memory, we have a function called define. So I can define let's define a thing called LST. List is the list 1, 2, 3. Now notice I'm writing it up here this time instead of writing it down below. When I write something up here, I can go back and edit it and change it. So this is kind of like me having my source code, saving it, then coming down below and running it. All right, as opposed to me typing something down here, which is a one-off. All right, so I would say most of the time, unless you're just experimenting real quick and you want to know kind of what a function does, you probably want to write your code up here. That way, when something isn't quite right, you can make little tweaks to it and not have to retype in the whole thing. All right, so I'll go ahead and define my list 1, 2, 3. If I hit run on this, I shouldn't see any output. Okay, but if I come down here and I type in LST, you see that it's remembered that list 1, 2, 3. Make sense? So it ran this code up here, and now the environment I'm working in down here is the result of the code that was run above. Okay? So now I can do things like the car of LST will give me the 1. The cdr of LST will give me the 2, 3. The car of the cdr of LST will give me the what? 2. Okay, the car of the cdr will give me the 2. That's the same thing as saying the car of the cdr of LST. So the cdr of LST will give me the list 2, 3. The car of the list 2, 3 gives me the 2. So these two lines right here are identical to each other. This is just the shorthand, or I sometimes refer to as the syntactic sugar version of this guy. I would recommend that you almost always use this format. If you're going to only go 2 levels in, like a CADR, you can do the combination. But any farther than that, I think you're probably playing with fire in terms of matching parentheses and stuff like that. Because technically, you could do the CADDR. So that's the cdr of the car of the cdr. What should that give me? What's the car of the cdr? 3. So I take the cdr of list 1, 2, 3, I get the list 2, 3. I take the cdr of that, I get the list 3. I take the car of that, I get the 3. Make sense? So a lot of what you'll be doing here is kind of wrapping these things together. Now, something I mentioned last time was this thing called a lambda. Well, the book will talk about it as lambda calculus, which just makes it sound scarier. But what's a lambda expression? I mentioned it near the end of class last time. What's a lambda expression? Okay, it's an unnamed function. And the parallel we were kind of drawing is, all these things are things we're already used to working with. And hopefully you experienced as you were doing the homework assignment for today that this is just kind of this new way of formally stating stuff that we already know to be true, right? It's not fun because somebody's trying to make something that actually isn't all that difficult sound hard by putting funny mathy names to it, right? We've dealt with variables in programming for a while. So even those of you who aren't fans of programming, in the big scheme of things, would you say that variables are probably one of the easier things? Like, oh, I could define an integer, set it equal to 5. That was it. That'd be great. Right? If that's all I had to do was define variables, life would be good. Now, even functions. Writing a function that actually accomplishes some logic, starts getting into the more difficult programming stuff because now you're actually using this foreign language thing to solve problems. Now you're doing two things at once, and it's kind of like juggling, right? Juggling while you're hopping on one foot, it becomes difficult. Okay, but in general, if you have the syntax for a function, so you have a function name, it takes in some parameters, it has a return type possibly in our strongly typed languages that we're used to dealing with, and then it has a body, the stuff that the function does. Also, not that big of a deal. Making it do something very, very specific might be a bigger deal, but just the idea of having like a function that just prints out hello world. It's not the end of the world, right? Now, the connection we maybe haven't made in the past, though, is the idea that whether I have a function name or I have a variable name, both of those are examples of having a name associated with value. Okay, if I'm defining an integer named a and setting it equal to 5, somewhere in memory, I'm creating a little spot, naming it a and putting the value 5 in there. If I have a function called do something, somewhere in memory, I'm creating a little spot called do something and I'm assigning a value to it. It just happens to be that that value is a function or a lambda expression. Okay, so an unnamed function is a lambda expression that we attach to a variable name. So for example, I can do something like this. So we create memory and scheme by using define. So I can define, let's call it add nums. This guy is going to be a lambda expression that's going to take in an a and a b, 2 parameters. Now you can put all this in one line, but you'll kind of notice that it's usually nicer to kind of press enter. It does some indentation for you. And we'll do an a plus b. And notice it'll kind of match the parentheses for you. So I'm defining here a variable called add nums. And that variable is going to have a value associated with it. The value associated with this guy is that dude right there. It's a lambda expression. Okay, a lambda expression starts off with the word lambda. Here's my parameter list, just like we would find in a Java function, Java method. So this guy takes in 2 parameters, a and b. And what am I going to do with them? Here's the body of that lambda expression. I'm going to, even though we didn't specifically talk about this, can we make a pretty good guess at what that function does? We see the plus sign. It probably does some addy stuff. So we're going to add whatever a and b are together. Now, what kinds of values are a and b here? And how do you know? What's your gut feeling? Go ahead. Okay, why?
Well, I mean, it's like.
Okay, so practically speaking, you're right. These are probably numbers. Part of the evidence is, well, you kind of named it like that. The other evidence is, well, you're doing some addition, so typically addition kind of works with numbers. So more than likely, these guys are probably numbers unless you're doing something really weird. Okay, but scheme is a loosely typed language. So we go back to when you first started learning about programming. Remember we talked about there's two kinds of programming languages, strongly typed languages and loosely typed languages. What's the difference? So which is Java? Java is a strongly typed or a loosely typed language? Strongly typed. And what does that mean? How do we know Java is a strongly typed language? Go ahead. You have to do fun things like put types in your variables. Yeah. So we are required to advertise the kind of value a variable was built for holding, right? Strongly typed. Same thing, we're also required to advertise the type of value the function will return. Now, which are faster, strongly typed or loosely typed languages? If we're looking at performance, strongly typed. Why? Okay, so why would it be slower if it doesn't know?
Because it has to go and find.
Okay, remember what that guy's called? The dude who's in charge of figuring out the kind of value? It's called a type inference engine. Type inference engine. So somewhere in a loosely typed language, which maybe from a programmer's perspective, we have to type less, and that's kind of good. But we also have to be, we're also allowed to be, or we're empowered to be more ambiguous in a loosely typed language. So now, we're maybe our own worst enemy or something like that. But because it's not requiring types, before this function plus is allowed to work, Scheme is going to have to go and figure out and make sure that both of these dudes are in fact numeric. That is types that this function can be applied to. Does that make sense? But as she said, if everything goes to plan and we call this guy addnums, presuming we're going to pass in some numbers, and we're doing some mathy stuff, and the end user kind of knows that, and they're going to send in two numbers here. Maybe A and B aren't the best variable names for that. If we really wanted to drive the point home, maybe we call this num1, num2. Something like that. Now we're, pretty much covering our bases. Where, if the user really, really, really wants to pass in a couple of strings or something to this, they could. But at the end of the day, we've made it pretty clear what we're expecting from them, right? All right, so if I go ahead and run this, notice nothing's going to happen, but we've defined two variables. We've defined a variable named LST, we've defined a variable called addnums. Now, addnums is a variable of type Lambda expression. And what do we do with Lambda expressions? We apply it to parameters. This Lambda expression requires two inputs. So I can do something like addnums to 3. So now I'm calling this Lambda expression, I'm applying it to these two parameters, which gives me a 5. That makes sense? All right, so now from last class, we were looking at one of the examples, one of the languages that dealt with we had a language, I think it was called S, a language S, and 0 was in the language, right? And then also we said that a value n plus 3, here I'm going to actually write this here. I'll show you the parameters, or I think this is a comment in this language. No, is it this guy? It might be that guy, but whatever. Let's write it in here. All right, so we might say that 0, the squiggly E guy, that guy. So 0 is in our language. And then we say that a number that's in the language plus 3 is also in the language. Something along those lines? Okay, so based on the homework assignment we did this last time, we pretty much know what this is kind of saying. So we have a piece of given information that 0 is a part of the language that we're describing by this stuff. Now at the same time, we're also saying that a number that is in the language plus 3 is also in the language. Okay, so if we just say it out loud, things like 0 and 3 and 6 and 9, these are things that are in the language. Okay, well now, what if we had to write a function for determining whether a certain value was in the language? We kind of have a starting point here where we know that 0 is in the language. Because we have to have some starting point, otherwise we're just guessing, right? But I want to write a function that determines whether a given number is a member of this language or not. Okay? So let's ask this question. I want to ask the question, is $15 in S? What do you think? Yes or no? Is 15 a member of the language S? How do you know? How'd you figure that out? Now we're talking about recursively specifying solutions. Go ahead. You wiggled a little bit. I assume you had an answer.
I would just say since 0 is the starting number, so you put that in for n, and then you just keep adding 3 to get to 15.
Okay. So you that's the way you solved the problem. You went forwards, right? It's like, okay, well, I know 0's in there. If I keep adding 3, do I eventually hit a 15?
Yeah.
That's what a person might do, right? Okay. Well, I want to write a function now that tests that. So what if I put it to you this way? What if I said, well, is 15 a value of this language? Do we know trivially that 15 is in the language? The only thing that we know trivially is in the language is what? 0. So that's the only thing we can just right off the bat answer, yes, 0 is in the language. Is 15 a 0? Nope. So how would we know if 15 might be in the language?
You subtract 15 from 3.
Okay, so we would call that same function again. I'd ask myself, well, I'm not sure if 15 is in the language because I only know for a fact that 0 is in the language. Okay, but I also have this other rule that a number that's in the language plus 3 is also in the language. So if I'm not sure if 15 is in the language, let's subtract 3 from it. Gives me a 12, right? And I'll ask the question, is 12 in the language? Well, you know what? I'm not really sure. Because I know that 0 is in the language, and I know that a value that's in the language plus 3 is in the language. So let's subtract 3 again. Is 9 in the language? Well, I'm not sure. 6 in the language. 3 in the language. Is 0 in the language? Yes. So since I did all of that stuff, I finally got to the end and decided, since this guy was in the language, then this guy's 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 in the language, and finally this guy's in the language. So I can give it a big thumbs up, right? What were we going to say?
So essentially you just assume it's in the language and then keep calling the function, having the function keep calling itself until you...
Rather than assume it's in the language, we're going to assume that we don't know, and we're going to pass the buck and ask the guy, ask myself the question. This is where the recursive calls come in. So if we were going to write this, we might write a define. Here, we'll steal this. So we're going to define, we'll call this guy in S. Kind of a naming convention for scheme functions. A lot of times if you're trying to, this guy is typically called something called a predicate. Your book will refer to this as a predicate. Which is a fancy way of saying a function that returns a Boolean. That's what a predicate is. A function that returns a Boolean. Usually it's for us testing something. Is something a character? Is something a symbol? Is something a member of this language? So a lot of times we'll put that little question mark. It's not a syntax thing. It just happens to be a naming convention thing. Because we're asking a question and we're getting a true-false answer. Make sense? All right, so we're going to define a function called ins. This guy's going to be a lambda function. It's going to take in a single value, a number that we're trying to determine if that guy is in the language, okay, by the rules we've set aside here. So this guy is going to take in we'll have it be a big N. That'll match what the book was kind of showing for your numbers. Okay, so we're trying to find out if a number N is in the language. All right, so now we get to the body of this guy. Well, if N is 0, it's in the language, right? All right, so now we need to be able to ask questions. Right, so just like we said before, all programming languages have the ability to remember stuff, have the ability to ask questions, and have the ability to do repetition. So let's ask a question here. So we're going to ask the question, if. We have a couple of different conditionals that we know how to write, but right now we're just going to deal with ifs. You'll see that most of the semester we're going to be using something called a cond, C-O-N-D, which is conditional. And that allows us to have multiple levels. Okay, so the way an if function works is it has a Boolean expression as the first parameter, and then what do you do if it's true? What do you do if it's false? So we're going to say if equal n0. If n is equal to 0, I'll give you a couple of precursors here as well. We're going to have 4 different kinds of equivalences. We're going to have the equal sign, we're going to have EQ, we're going to have EQV, and then we're going to have equal. And they each kind of mean, equal will always work, but it's inefficient. Just the idea would be equal looks at like bone structure. And that'll mean something to you later on. It's not really inaccurate to say that. All right, but right now we're doing number stuff, so we can stick with the normal equal sign. So if n is equal to, go ahead.
I just wanted to say that the semicolon is the comment.
Thank you. Okay, so if n is equal to 0, we know that 0 is in the language, right? So we want to go ahead and boil down to true. So the value for true in the language is $T. I believe it's a lowercase t, not an uppercase t.
I can remember the lowercase in both.
Okay. Well, we'll find out pretty quick if it screams at me. If it screams at me, I was doing it as an example for, but I haven't programmed in Scheme in 2 years. But it's like just like riding a bike, right? It'll come back quick enough. All right, so if n is 0, then we can say that, hey, this dude's in the language. True. Work is done. Now, if n is not 0, then what do we want to do? Well, we want to ask the question. Well, it's like, I don't really have a great answer for you. Okay, so I'm going to go ahead and I'm going to call this function again. I'm going to call it again, passing it a number that's 3 less than the current number, and see if I can make a decision based on that. Now, I only want to do that, though, if the number I'm going to pass it is going to be greater than or equal to 0. Because one little risk we have here is, let's say I was looking for the value, what I used before, 15, 14. We would actually get to a -1, and then we just keep going. Be -1, then -4, then -7, and we just forever. And then our program dies because we run out of memory and all that stuff. So we do need to control that we don't make a recursive call forever. We need to have a stopping case. So if I can't just 100% guarantee that the current value of n is in the language, I want to possibly check the previous value, the -3 value, but only if when I subtract 3 from it, it's a value that's greater than or equal to 0. That's the condition that I want to ask the question again. So my false condition here is going to be another if. So if minus n3 is greater than or equal to 0, if that's a true statement, if when I subtract 3 from the current value of n, I'm looking at a number that's at least a 0 or bigger, then I know I can safely call my ns again. So I'll call ns minus n3. Now I'm recursively calling the current function a second time, passing it the value that's 3 less than the current value. Now the else for this, if I couldn't just say that the current value is in the language, and I know that calling the function another time is not going to yield me a number that's in the language, then I know I've hit the end of the road. So I'll boil down to false. So real quick, let me show you and I'll pop back to the screen here in a second. Let's look at the syntax for the if function. So it's the word if, lowercase, followed by bool expression, followed by true expression, followed by false expression. And the false expression is optional. You don't have to have that. Now, this is no different than Java. In Java, I would say if, opening parenthesis, bool expression, opening curly brace, true expression, closing curly brace, then optionally else, opening curly brace, false expression, closing curly brace. These two mean the same thing, right? It's not like we're being introduced to this if statement for the first time. Just Scheme's syntax for it is a list-based syntax instead of the curly brace symbol-based syntax. Now what we've done here actually is we've nested an if statement inside of an if statement. We've said if something is true, do the true statement. Otherwise, my false expression in my current example, so I'm saying if, what did I say? I said if, well, we'll just go with that, equals n0, then I'm going to just boil down to true. My true expression is true. But my else is actually going to be another if. So the expression that's in my else is another if. And what I'm asking is if minus n3 is greater than or equal to 0, then do something else. Then I'll make the recursive call, so on and so forth. So I'm nesting functions inside of themselves. No different than if I was in a normal Java if statement. I could say if something is true, do this. Else, if something else is true, do that. Otherwise, do something else. I can have if statements inside of if statements in Java, right? This isn't something new. Just a little bit different syntax than we're used to working with. Okay, so does the if statement stuff make sense? All right, so out here, my function, well here, my variable in S, it has a value that's equal to a lambda expression that takes one parameter. For this one parameter, we ask a question. If the current value of the parameter is a 0, this guy's in the language, true. Otherwise, so here's the else of that guy. So otherwise, if the current value, when subtracted by 3, is greater than or equal to 0, then we know we can safely call this function another time. So there's my recursive call right there. So I'll call the same function, but instead of passing it the current value of n, I'm going to pass it a value that's 3 smaller than the current value of n. And we'll see if it can determine if that guy is currently in the language. Make sense? Now, if n minus 3 was not greater than or equal to 0, then I've hit the end of the road, just boil down to false. Now, notice that we're not actually saying return. Instead, what happens is we boil down to a value, which is the same thing, but if you're really comparing it to the languages that you're used to working with, you're used to at the end of a function saying, well, return true, return false, return some value of an integer. That's effectively what we're doing here, and you've heard me say it before in Java, that, oh, this function boils down to this value. Or when we're looking at the return type of a function, right? If a function in Java has a return type of int, no matter what we pass in, we know it will boil down to some integer, right? Okay, so that phrase, boil down, I guess it's my phrase. It's not something, well, that could be like Trump. I invented it just last week. It was great. It was great. But, you know, I've used that phrase often, so nothing's different here. We're just saying, hey, the return value of this lambda expression is false if I get here. So if I've fallen through all the little traps, think about this, and I don't remember if it's the Price or Right or what the other one, the Plinko game. So you keep dropping down through the stuff, and you get to the bottom, and you got nowhere else to go. That's the slot you landed in. That's the value we're going to return. Okay. So this lambda expression will evaluate whether a value n, a numeric value n, is a member of that language S if the language S is defined by the grammar where 0 is in the language and a number that's in the language -3 is also in the language. Make sense? So it's a complete fictitious language. So what effectively are we doing here? What's the purpose? I will test this guy real quick just to see it work. Lambda. So if I say in S15, we expect a true. In S14, we expect a false. Now that we've thoroughly tested it for every numeric value that exists, we can say it's good. Based on smiles, 2.5 people got that joke. You were the half. All right. So what's the purpose of this? Why would we ever do something like this? Because that is the challenge in this class, at least early on. Because as you were doing your homework assignment for today, one thing that you at some point probably felt like, well, this just feels like busy work. What the heck are we going to use this for? Right? Don't you hate that when classes just have you do stuff just because, oh, well, we want them to spend a lot of time on it. Just, it's kind of it's an act of suffering, right? But there's no punchline. Why are we doing this? Why did I just write a function to find out if some value is a member of some language that we've just invented that's a meaningless language? The counting by 3 language, the positive number counting by 3 language. This must be a microcosm of something larger, something more important in our programming universe. What are we effectively doing here? Go ahead. All right, so let me write something here. I'll attempt to fix the capitalization in a minute. All right, so in looking at that, is that a syntactically correct main method in Java? So I've had you guys memorize, well, we've left the public class part out, but this is just the main method, right? So in your previous classes, I've had you write the hello world program, the error-free hello world program. Does this look like it matches the main function from that? Error-free, perfect. How do you know? This goes back to your very first programming class when I asked you, how do human beings solve problems? Okay. And what was the thing we decided? We decided that we're so good at solving problems that we've forgotten, we have trouble articulating how we solve problems. So hopefully all of you in here have committed to memory the Hello World program. So you can look at that and you just say, yeah, that looks right. I just know it's right. I feel it. Okay, but now I want you to really evaluate it. How do you know that's right? Somewhere in your head, you have at least what's called an intermediate understanding of the Java syntax. right? What correctly written Java looks like. You recognize that as a symbol that's part of the Java language. You recognize this as a symbol that's part of the Java language that is allowed to come after this symbol. You recognize this as a symbol that's in the Java language that's allowed to come after this symbol. This symbol. You've recognized this as a symbol in the Java language, kind of a built-in name of a method. Open parenthesis, where when we see a method name, we're expecting a parameter list. Is that guy a parameter list? Does it meet the requirements of what we expect a parameter list to look like? Yep. Then we expect an opening curly brace. Well, really what we do is we expect a list of statements here. Well, we expect a statement, and that statement can be a list of statements. In this case, we do have a list of statements. That's how we represent it with the curly braces. So we say, yeah, this looks legal. I just happen to have one statement in here. And then this looks legal. This all looks good. But how did I actually do that? I walked through this. Let's call it symbol by symbol. Pattern matching. I decided as I walk through this one character at a time, have I run into any bumps that break the rules? Right? And as we did this, we had clean sailing. Okay? We didn't run into any bumps here that broke the rules. We have correct Java syntax here. Might not do what we wanted it to do, but it is accurately written Java syntax. What are we doing here? Doing the same thing. We're taking an input value, we're applying the rules of a language to it. And we're determining if it meets those requirements. The language is meaningless, right? I mean, I'm sure we can come up with something maybe for a 3 or 4-year-old or something like that where this language could be helpful. Okay? But in general, this isn't the language of counting by threes isn't something that we're going to find all that useful all that often. Okay? But it's a simple enough example. I mean, what if I had to write this exact same thing that determined, instead of passing it a single number, I passed it a Java program. And I said, does this match syntactically legal Java code? Do you think it would be a little longer than this? A little scarier than this? Now guess what? We're going to write that in here. That's your homework for Friday. Take this as your starting point. Now write Java. Now write Java. All right, so a lot of stuff that we're doing here is pattern matching. I had a student at lunch today, and he was sitting there actually talking to us, Tim was, and he was asking, he's in our grad program in computer science, and he was asking about the theory class, which deals with something called automata theory, finite state machines, Turing machines, things like that. Scary sounding stuff. That's the same thing as this. We walk from state to state to state to state, and when we run out of symbols to check, we ask ourselves, am I in a safe place? If I'm in a safe place, we're going to give a thumbs up and say this is good. If instead I'm in an unsafe place, I'm in a state where I don't have I'm not in a terminating state. I'm out in the middle of nowhere. We haven't finished the program, and I've run out of symbols to test. Then I give a thumbs down. This isn't good. That makes sense? Okay. So for Friday, what we're going to do is we're going to continue to practice our code, our scheme stuff. So I have to look up the exact questions. I believe it is question 1.15 and 1.16, the first two scheme questions in the book. Wherever I'll look it up, but the first one's called duple, I think, and then the second one is like remove first or remove element or something like that. As you write, you're practicing scheme. So I'll go look it up here real quick and I'll get it in there. But so you're going to write 2 scheme functions, 2 Lambda expressions like we just had here, and that'll be your assignment for Friday. Sound good? And then you should also be working on the Bible response for Friday. All right, I will see everybody on Friday.